The pressure readings on auxiliary control are fluctuating outside the acceptable parameters. We need to run the diagnostic again. The safest aircraft are not those that never detect problems, but those designed to continuously verify every system before flight. Look at the pressure levels on engine 3. It's fluctuating too fast.
The system data confirms the anomaly. We need to run the diagnostic sequence again.
The aircraft makes no sound of panic, yet the flight management system has just delivered data completely different from the aerodynamic sensor system.
The most frightening thing in aviation is not when everything fails, but when systems continuing normally.
While the previous flight history shows a spike right here. Let's cross-reference that with the vibration metrics at cruise altitude.
The silent space inside the maintenance hangar behind the terminal now feels more like a psychological analysis room than a repair facility. One system says the pressure is completely stable, while another shows a slight deviation large enough to trigger a high-level inspection process.
In modern aviation, aircraft no longer operate like single machines, but like networks of electronic brains, constantly observing one another.
That is why when systems begin to disagree, the first thing that appears is not chaos, but the tense silence of people who
The central question is no longer which system is correct, but what happens to the aircraft when components begin contradicting one another.
Under normal operating conditions, every system on the aircraft continuously exchanges data with one another, like a never-ending conversation between hundreds of sensors and control computers. Every signal on the aircraft is compared through multiple layers of verification before being allowed to influence flight control decisions.
If an airspeed sensor sends abnormal data, the flight management system immediately hit with wing angle of attack, pressure,
The workers aged 22 to 25 inspect every connection beneath the electronics compartment, because in aviation,
modern aircraft are designed with the philosophy that no system is allowed to become the single source of truth, because humans understand every device can become inaccurate under certain conditions. That is why an aircraft always contains multiple layers of cross-check systems operating simultaneously like independent specialists.
Under normal conditions, small differences between systems are handled silently inside algorithms without passengers ever noticing from the outside.
But that constant ability to challenge one another also creates a special danger when systems stop showing.
At that moment, the aircraft is no longer facing a simple technical issue, but a crisis of trust inside its own electronic intelligence structure. East Asian male engineer aged 25 to 30 begins noticing that vibration data from the left wing does not match the stable report from the aircraft's central load balancing system. The unusual part is that neither system reports any internal failure, making it far more difficult to determine which data source can actually be trusted.
The disagreement only appears at a certain altitude, where the outside temperature drops to extremely low levels.
No one in the team rushes to conclusions, because in aviation the most dangerous thing is trusting an explanation too early before.
The contradiction becomes clearer when the pressure sensor system shows slight wing oscillations, while the load balancing system. If the first system is trusted, the aircraft requires immediate structural wing inspection.
But if the second system is trusted, look, it's not random. The disagreement repeats exactly when the temperature spikes.
The environmental conditions confirm it. It's the heating cycle.
This transforms the entire issue from a simple electronic fault into the suspicion that the systems are interpreting the same physical phenomenon differently on the aircraft. And at that moment, the real question finally appears in everyone's mind. If systems observe the same event but interpret it.
The recently updated vibration analysis algorithm changed how the system interprets signals under extremely low temperature conditions.
Meanwhile, the load balancing system still uses the older evaluation model, causing both processors to receive the same data yet reach completely different conclusions.
This disagreement does not come from faulty sensors, but from systems thinking through two different logical frameworks that are no longer synchronized after the software update.
The male engineer aged 25 to 30 explains that in modern aircraft, software not only displays data.
That means the same tiny vibration on the wing may be considered normal under the old algorithm while being interpreted as a warning sign by the far more sensitive new algorithm.
The delta between the algorithms is widening at this threshold.
Noted. Continue recording the variance.
The aircraft does not truly panic when systems disagree because the entire aviation safety structure was designed long ago to prepare for exactly this kind of situation.
When conflicting data is detected, flight control computers often automatically reduce the trust level of disputement. If the disagreement exceeds allowable limits, the aircraft will trigger warnings for the pilots while returning part of the control authority.
This reflects a core aviation philosophy that automation exists to support humans and must never become unquestionable absolute authority.
The systems' ability to challenge each other helped the aircraft detect the issue before it became a real danger.
If every system used the same logic and agreed completely, the flaw in the new algorithm might have remained hidden through hundreds of flights without ever being discovered.
Paradoxically, that disagreement becomes proof that the aircraft is still intelligent enough to doubt itself before humans even recognize the abnormality.
A system that always agrees with everything is not necessarily a sign of perfection, but sometimes the most dangerous sign.
The male engineer aged 25 to 30 begins simulating a flight under extremely low temperatures to directly compare how both systems interpret the same wing vibration.
The results show that the new algorithm reacts faster to subtle changes, but also creates more sensitive warnings, while the old algorithm...
Neither system is entirely wrong because each prioritizes a different safety philosophy within the same complex operational situation of the matte gray narrow-body aircraft.
We prioritize detecting danger as early as possible. We prioritize avoiding false warnings that could destabilize flight operations.
The East Asian male and female workers aged 22 to 25 continue finalizing the new synchronizations.
The most important thing is not deciding which system wins, but ensuring that every system understands the same language of risk evaluation. Modern aircraft therefore do not operate based on absolute trust in a single brain, but on the constant debate between multiple layers of electronic intelligence. In many situations, those silent disagreements have saved the aircraft from continuing to trust incorrect data without anyone objecting.
The female engineer aged 22 to 25 slowly closes the final inspection session, while the workers aged 22 to 20
Happens when aircraft systems disagree is not immediate collapse but the activation of a deeper safety layer, where every piece of data must prove its own value again.
Modern aviation understands that mistakes can never be eliminated completely, so instead of trying to create systems that never fail...
That is why the safest aircraft in the world are not machines of perfect silence, but machines that continuously debate silently within themselves throughout every flight. Are these sensor readings within the acceptable deviation limits?
Yes, the data confirms the adjustment. Let's proceed to step 3.